Hello everyone. Today we are connecting two powerful ideas, the basic trigonometric ratios you learn with right triangles and the elegant, all-encompassing unit circle. Let's get started. We begin with a right-angled triangle and an acute angle theta. We define three primary ratios. Sine of theta is opposite side over hypotenuse. Cosine of theta is adjacent side over hypotenuse. Tangent of theta is opposite side over adjacent. A classic memory aid is SOH-CAH-TOA. It's all about ratios of side lengths. Crucially, these ratios depend only on the angle theta, not the triangle size. But here's the limitation. This definition only works for angles between 0 and 90 degrees. What about 120 degrees or 270? That's where the unit circle comes in. Meet the unit circle. It's a circle with a radius of exactly 1, centered at the origin of our coordinate plane. Now let's place our right triangle inside it. See the right triangle? The hypotenuse is the radius, which is 1. The adjacent side lies along the x-axis, so its length is the x-coordinate. The opposite side is vertical, so its length is the y-coordinate. Now let's plug this into SOH-CAH-TOA. If sine of theta equals opposite over hypotenuse, then on the unit circle, sine of theta equals y over 1, which is just y. If cosine of theta equals adjacent over hypotenuse, then cosine of theta equals x over 1, which is just x. And tangent of theta is y over x. This is a huge upgrade. Now, sine and cosine aren't just ratios, they are coordinates. And because we can find a point on the circle for any angle, we can now define sine and cosine for any angle. Let's travel around the circle. We start at 0 degrees. At 0 degrees, the point is 1, 0. So cosine is 1, sine is 0. At 90 degrees, the point is 0, 1. Cosine is 0, sine is 1. At 180 degrees, the point is negative 1, 0. Cosine is negative 1, sine is 0. At 270 degrees, the point is 0, negative 1. Cosine is 0, sine is negative 1. At 360 degrees, we're back to 1, 0. Look at that. Cosine, the x-coordinate, becomes negative in quadrants 2 and 3. Sine, the y-coordinate, becomes negative in quadrants 3 and 4. This elegantly explains the signs of the trig functions. But what about a familiar angle like 30 degrees? Its point is the square root of 3 over 2, 1/2. So cosine of 30 is root 3 over 2, about 0.866. And sine of 30 is 1/2 or 0.5, exactly what our triangle gave us. Now, look at 150 degrees. Its reference angle is 30 degrees. Its point is negative root 3 over 2, 1/2. So cosine of 150 is negative root 3 over 2, and sine of 150 is still 1/2. The unit circle extends the logic of the triangle. This is the most beautiful part. By plotting the sine value, the y-coordinate, as we go around the circle, we generate the sine wave. Similarly, the x-coordinate gives us the cosine wave. The unit circle is the source of these fundamental waves. From this circle, we also get a fundamental identity. For any point, x squared plus y squared equals 1. Since x is cosine and y is sine, this gives us the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. So let's recap. In right triangles, trig functions are ratios of sides, SOH-CAH-TOA. On the unit circle, they become coordinates of a point, cosine theta, sine theta. The circle frees us from the 0 to 90 degree limit, allowing definitions for any angle. It naturally explains signs, identities, and waves. The unit circle isn't a new set of rules, it's the natural, graphical home of trigonometry. Thanks for watching.